Oké. Nou, goedemiddag allemaal. Mijn naam is Dick Sterenborg. Ik ben gedeeltelijk verbonden aan de afdeling Biomedical Engineering en Physics aan het AMC. Ik ben een directe collega van Dirk Faber, die jullie natuurlijk allemaal goed kennen.
Dick, kan je het Engels?
Deel van
Dick, kan je het in het Engels doen?
Wat zeg je?
Kan je het in het Engels doen, alsjeblieft?
Ik versta je niet goed, sorry.
Kan je het in het Engels doen, alsjeblieft?
Oh, sorry. Okay, so I'm, as the slide says, a direct colleague of Dirk Faber, whom you know very well, of course, but the larger part of my time I spent at the Netherlands Cancer Institute at the Department of Surgical Oncology, where a group of some 20 physicists, clinicians, and medical physicists are working on the application of optical techniques in the operating room to improve the outcome of cancer surgery. Now, I will be talking about elastic scattering spectroscopy. And what does that mean? Well, spectroscopy is probably very well known to you. In the case of light, it just means that you separate all the wavelengths and you generate a spectrum. And then spectroscopy is in fact the recording of these spectra. And as Merriam-Webster accurately describes, it is not just measuring the spectrum, but also thinking about the physics behind it. Okay, now what exactly is elastic scattering spectroscopy? Elastic scattering is basically an event where a photon interacts with matter without exchanging any energy. So there's a lot of types of inelastic scattering, for instance, like fluorescence. You have a short wavelength, for instance, ultraviolet light, that is absorbed, and then a couple of hundred picoseconds later, another photon comes out in another direction, but it has less energy. Another example of inelastic scattering is Raman scattering, where the incoming photon exchanges energy with vibrations in the molecule. Also very interesting for diagnostic purposes, but it is inelastic scattering. And what we are dealing with in the coming hours is elastic scattering. And that simply means that the light that comes in has exactly the same wavelength and energy as the light that came in. And there's different types of elastic scattering, and I will talk about that later. In fact, it's happening right now. We have Rayleigh scattering that happens when the scattering particle, the substance that makes the photon change its direction, when it is much smaller than the wavelength of the light, then we speak about Rayleigh scattering. That goes with the fourth power of the wavelength. So that changes with wavelength very rapidly. Now, in the other extreme case, where the wavelength is much smaller than the diameter, then the scattering is independent of wavelength. And we know Mie scattering, and that is in between. So the power of the wavelength with which the scattering intensity changes lies between -4 and 0. And this is the dominant form of scattering in biological tissues. Okay, now here is one of my holiday pictures. Of course, it's always nice to have your holiday pictures in a slide, but I have a certain purpose with it. This describes everything. Now, at the beginning, we see in the corner here, we see the blue sky. The fact that the sky is blue has to do with the fact with this power of -4. So the 400 nanometer is scattered 2 to the power 4 times stronger than the red light of 800 nanometers. So the light that doesn't hit the earth but flies through the sky, the blue light is scattered towards my eye much stronger than the red light, and that's why the sky looks blue. Now, there's And also another very odd form of scattering is called rainbow scattering. I won't deal with that here. It's rather complicated, but it needs to be mentioned in this picture. Now, we see here scattering or even wavelength independent scattering, because the cloud is white. All wavelengths are scattered equally, and there's apparently no absorption because the wavelength independent scattering, when it reaches my eye, is still white. But here we see colors, and these colors have nothing to do with the scattering itself, but these are all these colors you see here are basically biological substances or substances of another nature that scatter light, but also absorb light. And the light that can reach our eye after scattering is not all the same as all the light that came in, but some wavelengths are absorbed, and that's why we see all these different colors. That simply means that are all different chemical substances. And that is very interesting. We also mentioned specular reflection here, that's light bouncing off the surface of the river. I mentioned that because that also comes on later. Now, takeaway lesson of this beautiful holiday picture is that without elastic scattering, we wouldn't see much. You can imagine how life would be without scattering. You'd be in the middle of an ocean. There would be colors, but you wouldn't see light unless it shines directly in your eye. Now, we see light coming from all directions, and still the sun is only on one location. We see light coming from everywhere because of scattering, and because scattering allows light to enter materials and come out after some absorption. We see all these colors. So elastic scattering is extremely important in everyday life. Now, I mentioned reflection. Reflection and scattering are very strongly related, but in biological tissues, we have basically three types of reflection. The first is specular refraction. That is reflection from the surface of the material, which is due to the fact that the index of refraction of the material is slightly higher than that of the ambient air, and then the photon samples roughly a wavelength deep, and the light is reflected from that very superficial layer. Now, the second type of reflection is subterfuge reflection. So all the light that is not reflected from the surface enters the tissue, but because the tissue has scattering, for instance, scattering, photons are changed of direction after a certain penetration depth. And when that reflection is in the backward direction, the light can leave the tissue immediately. We call that subterfuge reflection. And the sampling depth of that type of reflection is roughly equal to the scattering mean free path. Now, the third type of reflection is, for me, the most interesting one, and that's called diffuse reflection. So basically, your light is incident on the tissue, fraction is reflected, but most of it enters the tissue, is scattered around multiple times, and then leaves the tissue at some place. And because there's multiple scattering events, scattering is, the light is spread out in a sort of random manner through the tissue, and it will come out in many places at the same time. Now, the sampling depth, it depends on the geometry. So light that leaves the tissue very close to the source may have been only superficial, and light that has been is emitted from the tissue at a large distance from the source may have traveled much deeper through the tissue. And yeah, why is it so important for diagnostic purposes? Well, light that bounces off the surface doesn't tell you anything on what is below the surface. So if you want to buy this car, not only do you want to know the mileage, but hey, you want to check if there's an engine in there. You cannot see that from the outside. Now, on the other hand, here, we all see immediately what's going on. this guy has been in trouble. In fact, he bounced off his motorbike and fell on his shoulder. And a few days ago, he had a big bruise. There was some veins that started bleeding in the skin. Blood leaked out of the vessels, and gravity took it slowly down. Here you can see some intact hemoglobin, but in the course of time, the blood has changed position. But during that time, also the body started breaking off the blood that didn't belong there, and made all kinds of intermediate chemical products like bilirubin. And bilirubin is much more lipophilic and it sticks to the fat, so the yellowish color remains behind, and there's still some blood in this region. Here it's even getting green. That's biliverdin. That's another chemical. And basically you see a whole bunch of chemical reactions happening inside the tissue. And that's possible because the light entered the tissue, was selectively absorbed, and some of that light came out again, and in this case to a camera or to our eye, and we can distinguish these colors, and then you can see these different chemical substances. Something similar went on here. You see that gravity takes the blood down, and in its way down, there's a lot of yellowish and greenish colors of the intermediate products before all the blood is broken down and the bruise disappears. So diffuse light has been inside the tissue and tell you something on what is going on in the tissue. And that is a diagnostic concept that is as old as mankind. There's stories of thousands of years ago on how to react on these yellowish colors, what is going on, which drugs you have to use. It is part of medical diagnostics as long as we have medicine. Okay, so in summary, why is elastic scattering interesting? It turns photons around inside the tissue. It gives the eye of the observer light to look at, and it's relatively easy to measure. We can see it with the eye, and then we can have all kinds of interesting devices to quantify it. Now, scattering also determines the light distribution, where the light has been. I will show that in a minute. And scattered light that comes out has been inside and has taken up information on the chemistry and the physiology of the tissue, inside the tissue. And elastic scattering itself is also a tissue property that may be used for diagnostics. Okay, now we do a simple experiment. I told you scattering determines where the light goes. Now we have a simple tabletop experiment. This is a coffee pot that you use for an electric coffee maker. Here we have a little laser pointer and a piece of white paper and some milk, low-fat milk, because that's more healthy, of course, but for this experiment, it doesn't really matter. Okay, what we do first, we have our coffee can with only water in there. Now here you see the piece of paper, and here is the laser pointer. You see some reflections in the glass, and because it's not an expensive optical glass, but just household glass, light is bounced off even to the bottom of the vessel. That's not interesting. Let's forget about this. You see here some light at the surface, and you see the main portion of the light exiting on the other side of the coffee pot on the white screen. That's obvious. Now I put in a little drop of milk, and then suddenly everything changes. I suddenly see a light beam. I couldn't see the photons traveling from here to there, because to see a photon, it has to reach my eye. Photons that go here through the water where there's no scattering are invisible to me. They're invisible to me until they hit the paper and are scattered in all directions. With a little milk in there, the liquid becomes slightly scattering, and from time to time, photons are scattered in all directions, so also in the direction of my eye. That's why I can see the beam. And the fun part is that if I increase the scattering, you will see the beam increase, but you also see it attenuate. So it's thicker here than it is there. That's yeah, I think an optical illusion, but it's just less intense here than it is there. And you can also see there is no hotspot anymore. There's a faint little spot on the paper, but most of the light never reaches the paper and has been scattered around here. Now, if I go on and on and on until all my milk is gone, I no longer see a light beam. And we learned geometrical optics in high school with lenses and beams. And in tissue, you don't have light beams. You have a diffuse blob of light. It's like a big fog cloud. You cannot distinguish anything anymore. Now you can see that scattering determines where it goes. With very little scattering, it goes straight through. With a little scattering, it's still spread out over a large area. And with lots of scattering, it stays under the surface of the tissue in this case. Now, when I magnify it, you can see here, this is the glass vessel, and here you see the milky liquid that scatters the light, and here you see the source. So the light comes in from above, it is scattered, light that is scattered once or twice, leaves the tissue close to the source. We call that subterfuge reflection. And then when the light bounces around multiple times, it gets completely diffuse, and we mean with that the light loses its feeling of direction. It goes in all directions, and it can leave the tissue at multiple places distant from the source. Okay, and you have similar behavior in real tissue. Here we have a chicken fillet and a steak, and we've put some optical fibers in there, and you see that you get this beautiful diffuse blob of light inside the tissue. Now, you also see that how big this blob becomes is strongly dependent on the type of tissue, which means that when there's more blood absorption, for instance, in the steak, the light is attenuated more. And you also see that it is depending on the wavelength. So red light penetrates deeper than green light, and in a steak where there's a lot of blood, which is strongly absorbent for green light, you have the blob is extremely small. Now, this inspires you, of course, to start thinking about optical diagnostics. I can make a device that sees the difference between steak and chicken fillet. Maybe I can do more with it. So human tissue is highly scattering and reasonably transparent. You don't have that idea in daily life because we look at the surface. Here you see my hand, and in my hand I have a little red LED with a battery, and you can see some light come out on the side, but it doesn't come out here, or at least that's what you think. I don't see it come out on the surface of the hand because there's so much daylight that blinds my vision. Well, it doesn't blind my vision, but it's much stronger than the light coming through the tissue. But if I switch off the light in the room and I make the same picture in the dark, you can see that the light comes through the entire hand. And that is what gives us the opportunity to do optical diagnostics for several millimeters up to a centimeter deep in tissue. When there's a superficial blood vessel, you see the shadow of that blood vessel, but you can't see the bones. And that is because the light is so highly scattering that, it just bounces around the bone and you no longer see it. So you should really see diffuse light as an immense, strong fog bank where you have no details available to see, not much details. Okay, now the problem of optical diagnostics is to do quantitative measurements in this type of environment, and that's not easy. Now, why would there be clinical interest in spectroscopy? Well, of course, you want to diagnose stuff, you want to monitor, you want to classify tissues, and optical technology is relatively cheap and simple. It's much cheaper and simpler than an MRI. It's harmless. I mean, photons don't make you fat. They're not ionizing. They don't give you cancer. So light is everywhere all day. So if you can use technology to use that light to do the spectroscopy, that would be very interesting. Okay, so the general idea: we illuminate a patient. We have a spectrograph, we have a computer that records it, and we generate a spectrum. Spectrum can look something like what we see here. So there's wavelengths from the blue to the infrared. You can do, of course, much more, but for practical reasons, we usually limit ourselves to these wavelengths. That keeps the equipment easy. Of course, you can do much more nowadays, but for clinical application, you don't want optical tables, huge labs, etc. You want small, compact, portable equipment, and this type of spectra are possible nowadays with relatively simple equipment. And then you need an algorithm to tell you what the spectrum does. Now, and there's many things that look like the disease that are not the disease. And so there's many things that can generate spectra that look like this, but are not what you're looking for. So the algorithm is quite a challenge. Now, let's first think about what we expect of a spectrum. Why do we think a disease, any kind of tissue change would generate a change in the spectrum? Now, a disease, like any other biologic process, can change tissue physiology. So that would mean the amount of blood would change, the oxygenation of blood vessels would change, the size distribution might even change, and we could have differences in cellular energy state. So cells working hard have different chemical components than lazy cells. And there's, of course, the change in chemistry. Change in chemistry doesn't usually happen that rapidly, but if you have, for instance, the cancer process that may take months or years to happen, you could see differences in chemical composition, and different chemical composition may mean different chemicals that are optically active, or even that a certain chemical compound changes chemical state, like you saw in the bruise, where the hemoglobin was slowly taken apart to bilirubin and biliverdin. But what also happens is that the cellular architecture may change. So submicroscopic particles in the cells, how they are arranged, may change. Especially in cancer, one of the things that the pathologist looks at is how the nucleus is behaving. They're all things that may have an influence on the optics. Now, what we do know is that a number of these things have a direct influence on the absorption. So the concentrations of absorbers, the chemical states of these absorbers, oxygenation of blood is the same as the chemical state. When oxygen binds to blood, the blood changes color subtly. And when blood vessel distribution changes, there will be more blood. It will be in different size vessels. That also changes the absorption. And we know the cytochromes that are involved in energy transport to cells. They have a particular absorption spectrum that may change. And we know that scattering has to do with variations in refractive indices in cells. So a nucleus is more dense than water, for instance. So a nucleus will scatter. But a nucleus has a few micron size, so it will scatter wavelength independent. But you can see all kinds of small membranes in membranic structures in the cells. They will also scatter, and they are much smaller, and they are expected to generate me-scattering. And this architecture of these microscopic or submicroscopic, because you cannot really see them with an optical microscope, but the architecture may change during disease processes, and we might be able to detect that because of changes in the scattering. Now, a number of absorbers that are abundantly present in tissue are listed in this graph, and you see that there is a lot of subtle differences in the spectra. So if I do spectroscopy, I may see all these little signatures, and it would be nice if I could pull them apart and turn them around into a chemical composition, for instance. Now, how do we measure spectra? We have two main ways of doing that. The first one is with fiber optic spectrometers. Why fiber optics? Well, especially in the operating room where everything has to be sterile, you don't want to stick a spectrometer and a light source in the surgical wound. You want to keep some distance, and you can bridge that distance with fiber optics. Fiber optics are known to medicine because they are used for laser surgery, and fiber optics can be sterilized. And so using fiber optics, you could do reflection spectroscopy, for instance, very nicely in a setup like this. But of course, it is important how exactly you do it. We have two kinds of geometries. One we call diffuse reflection, where you have a source fiber and a detector fiber at a certain distance, at a certain minimum distance, where you collect photons that have been bouncing around for some distance, and you know that there's sufficient scattering events to make the light nicely diffuse. But you can also have the source and the detector very close to each other, or even use the same fiber to do it. And then we talk about subterfuge reflection. And then you're sampling very superficial to the fiber, let's say a couple of 100 microns deep. And here, in the other situation with diffuse reflection, you're sampling millimeters to a centimeter deep. So that gives you some leeway in choosing what you want to see. So the sampling depth is mainly determined by the geometry. Now, the second way of doing it, and that my second part after the break of my talk will deal with, that is what we call hyperspectral imaging. So those are cameras. A regular camera gives you a value for red, green, and blue, just like the human eye. Hyperspectral cameras give you as the whole spectrum for each pixel. Those are expensive cameras, and they're not very fast, but we have them in the visible region, but also in the infrared, and they're very handy in searching for deviations over large areas. While the fiber optic approach is really a point measurement, where you sample a small volume, and you really have to know where you're looking for, because otherwise it's really the needle in the haystack approach. Okay, but the second part of my talk will deal with the hyperspectral imaging, and I will now continue with going to the fiber optic approach. Now, the general idea was that you have an algorithm that knows how to interpret your spectrum, and that is not so easy. But the common approach to classification nowadays is you make a big database. So you have a piece of tissue, and on that tissue you measure a spectrum. You take a sample and send it to the pathologist. After you pay the bill, you get your diagnosis, and you make a big database. Now, with this big database, you train an algorithm, and because most optical spectra are hugely oversampling the information there is, the simplest spectrometer has 2,000 pixels, and if you can look at the features you see here, those are they contain 20 pixels or 50 pixels dealing with one feature. So you're grossly oversampling the physical phenomena happening in the tissue. So you need, if you leave them in your data set, you may start to overtrain your algorithm. So we do what we call feature reduction, and machine learning experts have all kind of semi-smart ways of doing that. But once you've trained your algorithm, basically any spectrum taken in the patient will immediately lead to a prediction of a diagnosis. And then it depends on the doctor to believe you or not believe you. But this is the standard technique nowadays. So the big question remains, where is the biomedical optics in all this? Well, not necessarily any. If you see a spectrum just as a bunch of data, then you can do AI and you probably get a nice result. But as I said, there is a big risk of overtraining. If you just look at these 2000, sometimes with fancy spectrometers, even 4000 pixels, if you see them as independent pixels without any interpretation of the data, then the risk of overtraining is very large. If you do feature reduction without using your brain, you may be throwing away data. So it's really challenging to optimize between overtraining and throwing away essential data. And so, in addition to that, there will be some problems in your database. There will be measurement errors. If you do a measurement on a piece of tissue, how controlled is that? There may be pressure artifacts, there may be hasty doctors that pull the fiber away before you push the button. There will be equipment noise that has nothing to do with the tissue. So there is a lot of variability in measurements, and there's also variability in between patients and inpatients. So machine learning as a black box, if you do not take care of those errors, they will be using all these random errors to improve your results if you're not careful. So the nice thing about biomedical optics is that we understand spectra. We know a lot about tissue scattering. We know a lot about absorption spectra. We know a lot about diffusion of light, of reflection of light. So with that, we can make a model that uses all the a priori knowledge we have on the problem. So everything we know about biomedical optics and everything we know about the biology of the problem. Because if you're looking at cancer, you're looking at something else than when you're trying to detect measles. We have knowledge about what we are looking for. And so if we can put that in a model, and that's so we can generate, for instance, from 10 to 15, it could be 50 parameters to generate a spectrum, then we have a relation between all these physical and medical features that turn them into a spectrum. And that's called a forward model, where your knowledge is used to generate an observation. And then you need an inverse model to interpret your observation into your medical and physical features. The nice thing about this is that your model based on medical and optical knowledge will not have noise, will not have errors. It will only generate legally possible spectra. And it can distinguish between measurement errors and noise and the real phenomena happening in the tissue. So that is very important. Now, how do we make these models? Now, there's two ways of doing it. When sometimes we are lucky, especially when the light is purely diffuse, and when it's really diffuse, then we can use diffusion theory, and that is an analytical mathematical model. It looks complicated, but yes, once you have programmed that in your computer can generate a spectrum from any set of parameters within a flash of a millisecond. Now, another way, when you do not have an analytical model, you could use Monte Carlo simulations. Now, Monte Carlo simulations take a long time because, yeah, you have to simulate all possible events. An intermediate way of doing it is to do an extensive set of Monte Carlo simulations of all possible situations, and then try to make an empirical model of it. That's how we usually tackle the subdiffuse situation, where diffusion theory is not valid, but where 100,000 or 1 million Monte Carlo simulations show you that there is a simple analytical behavior between the parameters and the spectra. And then you have the very complicated situations where there is no analytical modeling possible. And then you can use lookup tables. But yes, especially in when you have 15 parameters, you have a 15-dimensional lookup table. It takes a long time to find your way in those, but it's technically feasible. Now, the problem we have to solve is that we have a spectrum. We want to do some feature reduction. And then, we have a spectrum and we want to generate our parameters rather than the other way around. Now, when we have an analytical model, it's very easy, even if it's an empirical model, it's very easy to generate an inverse model. That is just mathematics. Monte Carlo simulation doesn't go in the inverse. And again, the lookup tables is in fact the inverse way of finding the proper Monte Carlo simulation for your spectrum, but it can be very time consuming. Now, so the inverse problem is a very tricky one. You should realize that it is a 10 to 15 dimensional problem, and it is not a simple linear problem. What you have is that there may be multiple situations that have similar solutions. And it is also very sensitive to noise and errors. So, yeah, it is a tricky situation. Now, let's move forward. Let's go to analytical modeling. Now, you've seen the pictures of the milk in the coffee jar. Here you see a picture of an optical fiber carrying white light into my skin, and you see this beautiful halo around the end of the fiber. Now, that is called spatially resolved diffuse reflection. So you see the diffuse light close to the fiber. It's probably subdiffuse light coming out of the tissue, but you also see the colors change. Now, that is a very interesting phenomenon. For each wavelength, you have a certain radial fall off of the reflection. And from that radial fall off, it is possible to extract the scattering and absorption properties. Now, this is a nice model, which is it's 3 decades old now. It looks very complicated, but again, if you suffer half a day and program it in your computer, then it works. So it's relatively easy to do, and it gives you the reflectance as a function of the distance for your reduced scattering coefficient and your absorption coefficient. Now, this is, again, is easy to do. The only point is when you have a spectrum, you have to repeat this for all wavelengths. And then if you incorporate the fact that your absorption spectrum is not 2 or 4,000 independent absorption numbers, but is the sum of a number of known absorption spectra. We know all these components: water, fat, blood, bilirubin, hemoglobin. We know them. We have characterized them in the lab. We know the exact absorption spectra. And the absorption spectrum of your tissue is nothing else than the sum of all these basic spectra multiplied by their concentration. And for the Mie scattering happening in the tissue, we use the equation that I've hinted to before, where you have a wavelength to a certain power plus an amplitude factor. So we will be talking about the the amplitude of the Mie scattering and the slope of the Mie scatter. And you should remember that B is -4 when it is extremely small scattering particles, is 0 for very large scattering particles, and is somewhere in between most of the time. Now, with this, you can make a model that based on your two scattering parameters and your concentrations of your absorbers, that generates a nice spatially resolved diffuse reflection spectrum. Now, if you then measure these spectra, you can fit the spectrum on the model, and that fitting is basically replaces the inverse model. So we have a forward model, and we have a smart computer program that tweaks the input parameters until the measured spectrum and the model spectrum are similar. And this is a very ancient technique that works very well. As an example here, we see the blue is a measured spectrum, and a few of the parameters are listed here. You can see them change during the fit, but this is how one of our early models worked in real time. So you see that, you know, it fits very nicely. Not perfectly, but within the measurement noise. So basically, the trick is to not randomly, but in a smart way, vary the input parameters until the spectrum is close to the measured spectrum. And there are some ancient algorithms to do that. Levenberg-Marquardt is one, and that dates from the time that the old physicists and old mathematicians from the 18th and 19th century had to do all calculations with ink and a feather. So if they would do an iterative calculation, they would think very carefully before they would start. And these algorithms are implemented in MATLAB routines, and as you can see, they work extremely well. So this way, when we have an analytical model, we can fit that model on any measured spectrum within seconds. And that gives us basically a reduced data set. That is a nice way of doing intelligent feature reduction, where we use all the prior knowledge we have. Okay, but as I said, diffusion theory is valid for a homogeneous medium, and it should be semi-infinite, so you shouldn't have any boundary effects. Now, semi-infinite is not highly demanding, because scattering, as you could see in the coffee jar with milk, scattering limits the penetration of light to a number of centimeters, so it doesn't have to be a kilometers large sample. It can be centimeters, but it should be homogeneous, otherwise the model won't work perfectly. And if you look back at this spectrum and you see it fit, you see that there are some shortcuts taken by the model here, and the same here. And I personally believe that has to do with inhomogeneities in the tissue. Okay, but a patient is never homogeneous, because an homogeneous patient would have no biology. But tissue variations on a scale smaller than the optical diffusion length have no influence on light propagation due to scattering. So basically, everything you see under an electron microscope is just invisible to scattering and doesn't give us any problems. Tissue variations on a much larger scale do have influence on light propagation. But as I said, your source detector distance, your geometry, influences your sampling depth. And as a result, source detector differences in the order of 2 to 3 millimeters, you are in the range where the diffusion length is roughly determining your sampling depth, and that means that inhomogeneities do not influence your spectra. If you take your source and your detector very, let's say 2 centimeters, then basically when you apply a diffusion theory, you will be asking how gray is a checkerboard? And there's no answer to that question. The model cannot handle that. The diffusion theory will fail there. And at intermediate source detector distances, those errors will be very limited. At very short source detector distances, you have the problem that there is diffuse light that has traveled to the tissue, but the signal is dominated by photons that bounced around just once or twice, and they're not diffuse. So there we need another type of empirical model, but not diffusion theory. Okay. So as a clinical example, I will give you, we've done a couple of years ago at the NKI, the spectroscopic guidance during breast biopsy. So when a patient is diagnosed with a suspicious lesion on an X-ray, in X-ray screening, or the patient feels a palpable lump in the breast, then you go for a more thorough investigation. They look with ultrasound, and when they see something they don't like, they do a ultrasound-guided breast biopsy. The problem with these ultrasound breast biopsies was, it no longer is, but was that in about 10 to 15% of the time, the sample you get from something that is definitely a tumor contains normal tissue. And that is because ultrasound images are not very sharp. And it's not always easy to manipulate the fiber exactly into the lesion. Now, the quality of the ultrasound has improved over the last decade. And this problem is now not so important anymore. But originally, we tried to do this. Now, we had this specially manipulated biopsy needle. In principle, the biopsy needle is a hollow needle with a core in it, with a little empty space. So basically, you stick the needle in the tumor, and then you push a button here, and this front part shoots out very rapidly and cuts out this part of the tissue. So it goes in, and this tissue falls in, and then it retreats, and then the sharp point of the outer needle cuts the tissue off, and this piece of tissue, this little worm of tissue, goes to the pathologist. Now, what we did is we put 2 optical fibers in here, 1 source and 1 detector, and we plan to do a measurement before each biopsy sample. And what happened is that basically it looked like this. Now, this shows you how difficult ultrasound-guided breast biopsy is. Believe me, the tumor is here, and believe me, the needle is here. Here it is far away from the tumor. It's in normal tissue, and then you get the green spectrum. This dip is fat absorption, and it's very steep. Now, in the second case, the needle is close to the tumor, but not in the tumor, and you get the orange curve, and you already see that the fat absorption dip is much smaller. And in the third case, the needle is inside the tumor, and then you see the fat absorption dip is completely gone. Now, this is an extreme case where optical diagnostics is fundamentally simple, because breast tissue is usually very fatty tissue, and a tumor is growing from a milk gland, and milk glands are small channels with an epithelium, so it's just a layer of 1 or 2 cells that keep growing and peel off just like your skin. When a tumor happens there, these epithelial cells start dividing and dividing and dividing and form a mass. And this mass pushes away the normal tissue, which contains a lot of fat. So logically, the tumor contains not much fat, and that's what you see here. Of course, you have to be sure you're dealing with a tumor, because if you would blindly stick a fiber into a patient, and for instance, you would stick it in the muscle, you wouldn't see any fat either, but it would certainly not be cancer. So in this specific situation, where you are reasonably sure that there is some tissue that might be cancer or not, your fat dip will help you finding the tumor. So we've done a whole series of patients, 29. We did a whole number measured a number of spectra in normal, in edges, in the center of the tumor, made this little diagnostic algorithm, and with an accuracy of 88%. Now, that's not Nobel Prize winning, but it has a reasonable sensitivity and a very good specificity, which means that if the machine raises the red flag, it's usually right. Well, and with that, we started to do to see if we could guide the person doing the biopsy. Now, basically, in the first patient, so we had an algorithm that tells you normal, 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 going bad, now we're in the tumor. And then, of course, from the medical ethics committee, we were not allowed to tell the doctor what was going on, but we could see it. And at the end point, the doctor decided to take the biopsy that was sent to the pathologist. So this was going on in real time, in front of our eyes, blinded to the doctor, and you could see there were 3 biopsies taken in this patient. So there was three tracks, and in all 3 cases, the biopsy was taken also by the clinician on the moment that the needle was really in the tumor, and that is confirmed by the pathologist. It was invasive ductal carcinoma. Now, the second case, again, there was some weird event early on in the procedure, but then it went on, and then there was no signal for some reason. But again, when the doctor decided to take the biopsy, we were happy because our algorithm says this is cancer, which was confirmed by the pathologist. But patient number 3, where we investigated the guidance, we saw that we were going towards the tumor, so they were not completely wrong, but the biopsy was taken at the edge of the tumor. And here we do see invasive ductal carcinoma, but very sparsely. So it's not the bulk of the tumor, and there could very well be a different type of tumor in the core of the center of the tumor. So you could say, although this was not a false positive, it was not taken in the right location. So your quality of your biopsy would be better. But again, there's no real market for this anymore because the ultrasound quality has improved so much that these situations where you miss biopsy are no longer happening very frequently. But for us, it was very encouraging because we could prove that our technology was doing something very useful. So now I'm going to take a small break, some 10 minutes, and then I will start my second half speaking about hyperspectral imaging applications that came out of this. Okay. So I will be back, let's say 14:35 in 10 minutes. Okay. Then now for the second half of my story, hyperspectral imaging. Hyperspectral imaging is done with special cameras. So that allow you to make a what they call a hypercube of a piece of tissue, of a surface area, where for every pixel you have a whole spectrum. So not just RGB, but a whole spectrum. So let's say 300 or 400 values per pixel. And that can be done in different ways, but basically the most common approach is a push broom, what we call a push broom camera. There you do not image the entire image, but just a line of the image. And that line is split through a dispersive element into a spectrum on the camera chip. And so basically in the X direction of the sample, you have a number of pixels that you image, number of pixels on the subject that you image, and in the Y direction you project your wavelengths on your camera chip. This way you do not get an image, but you get you take a line from the sample, turn that into a 2D image where you have the X direction and the wavelength direction, and then by scanning either the camera or the chip over the sample, you can get the third dimension, which is the Y direction, and that gives you the three-dimensional hypercube. Now, sounds complicated. The hardware is pretty complicated to make, but yeah, we don't make cameras ourselves anyway, so it's a matter of spending money. Here's an example of how this would look. So you have a lens like a normal camera, but behind the lens is a slit. So it images only a line on your subject, and that is spread into, so every pixel from that line is spread into a whole spectrum on the chip. And then, for instance, with this camera, you need something that moves your sample in the second dimension, so your imaging line covers the entire area. Now, for instance, that could look like this. The samples that we imaged in our setup were done with such a push broom camera and with a mechanical scanning system. Very simple for experimental use, for research. Impossible to image a patient with a thing like this, of course. But hey, let's worry about that later. Now, you could do, you could imagine a different type of hyperspectral camera where you do not use a push broom, a line scanner, but where you have a camera that is sensitive to a broad band of wavelengths, and you have a light source with a programmable filter, for instance. That's another way people try to do this now. And then by taking an image at each wavelength that your programmable filter is set, you also generate your data cube. In this way, wavelengths are acquired one by one, and in the previous setup here, your lines are acquired one by one. It is technically different, but it's still a time-consuming procedure to do this. The third way, it's a hyperspectral snapshot camera. It's really not hyperspectral. We tend to call this multispectral, but basically because our cameras have huge amounts of pixels nowadays, and the resolution we require for diffuse light is not so high, so we can easily sacrifice pixels. And for instance, there are cameras on the market now where each group of 16 pixels have different wavelength filters, narrowband filters etched on them, very complicated stuff. So basically your resolution goes down to 250 by 500 real pixels. Okay, now that gives you, the nice thing about that is that that gives you the 16 wavelength bands in one shot. So it's much faster. So this would be ideal for taking a snapshot of a patient. It has reduced spatial resolution, it has reduced wavelength resolution, but it's increased speed. At the moment, we do not use this type of camera because, in fact, we do not know which wavelengths we need yet. You can buy cameras with equidistant wavelengths, but they may not be optimal for the problem we are looking after. So basically, this may be the future after we found out which exact wavelength you need for an optimal diagnostic algorithm. But that's the future. Okay, there is a fundamental difference in the optics of hyperspectral imaging and fiber optic spectroscopy. Now, basically, when you do fiber optic spectroscopy, you have a source and you have a detector at a certain point. So why is it so different than with hyperspectral imaging? Hyperspectral imaging just has a whole range of detectors on the surface simultaneously, basically the pixels that are imaged by the lens. Yet the pixel here, the area here that is imaged on one pixel, collects light not just from this source detector distance, but also from that one and from that one. So basically, hyperspectral imaging acquires a mixture of subdiffuse, diffuse, and diffuse reflection with extreme distances, which is very sensitive to inhomogeneities. So basically, this could be the ideal 2 millimeter distance between source and detector that would cater to diffusion theory nicely. Now, this would be way too big and would sample all kinds of inhomogeneities, and this would require an empirical model because it's subdiffuse reflections. That mixture makes the analysis of the hyperspectral imaging much more complicated. Diffusion theory is not simply valid. Okay, so the second point is that because of this, and because these sampling depths are not just dependent on the geometry, but mainly on how these different geometries are weighed, and the weighing of these geometries is determined by the attenuation of the light, and that is determined by optical properties. So basically, if I have a spectrum, then different parts of the spectrum may sample different depths, and that is much less the case in fiber optic spectroscopy. So in hyperspectral imaging, you have that complication. Okay. Now, another difference is that you may have surface reflections here. So when you have your source and detector fiber separate by a big distance on the tissue, you will never have surface reflections, specular reflections. On the other hand, if you just put a lamp on tissue and you look at it with a camera, you're very likely to see some surface reflections. That adds to the spectrum. Now, then there's another issue, and that's called glare. Now, when we have diffuse and subdiffuse reflection, light bounces off, light goes into the tissue, scatters around once, twice, or multiple times, and comes out in all kinds of directions. Now, specular reflection, the light doesn't enter the tissue, but bounces off, like from a mirror, in a predetermined direction. It's easy to avoid this by putting your camera under a smart angle so the surface reflection misses you. But glare is a phenomenon where the surface reflection generates light in all kinds of directions. And how does that work? Well, basically, if you look at a piece of tissue, it is never flat like a mirror. So you have surface reflections on a microscopic scale in all directions because the surface orientation is in multiple directions. So basically, you get a diffuse looking reflection from your surface that you're not interested in. Now, examples of specular reflection, diffuse reflection, and glare are given in these three pictures. Now, diffuse reflection gives you an integrated information about volume somewhere in this fog cloud. Doesn't give you much spatial information, but it does give you information on what happens inside. Now, specular reflection, again, tells you nothing about the mileage of this car, only how well the lacquer was polished, gives you something information about the surface of the car. Glare may give you the impression that there is some scattering going on, but actually there isn't. It is just a rough surface that reflects the light in all kinds of directions. And that is what we see in hyperspectral imaging all the time. Now, for instance, when you look at this finger, now you see differences in color because this was a guy that got stuck with his finger between the door. Very interesting from a medical point of view. The optics is clear. There's increased perfusion in this finger, so you see more intense red color, more blood. But what we also see throughout the finger is this whitish reflection. Now, the whitish reflection, that is glare. And why is it white? It is white because it is specular reflection. It is just specular reflection on a bumpy surface. And specular reflection is determined by the Fresnel equations. Now, the Fresnel equations are given in a simple form here, under 90 degrees. Under other angles, it gets slightly more complicated, but it's the same idea. It depends on the refractive index. And if you look at the reflective indices of, for instance, water and air, and then calculate the specular reflection coefficient as a function of wavelength, you see that it hardly changes over a large wavelength range. So that is why surface reflections here look whitish. Now, is that a problem? Well, you have a similar phenomenon with fat and water, and it's a little higher, but it's still very wavelength independent. Yeah, the specular reflection intensity may contain information about tissue composition, but to do this glare measurement in a quantitative way, so we can determine the absolute value of the reflection coefficient of the refractive index, that's not very easy to do because it also depends on how curved your surface is. So we may not be able to get the exact tissue composition from the glare, but it's certainly a phenomenon that we have to deal with, because if I just have tissue of very strongly varying composition, I see these spectral differences. But if I have a piece of tissue that is homogeneous, but it has a rough surface structure, then the glare will vary strongly with pixel, and then my glare will manifest itself as an offset over my diffuse reflectance. So I will see identically looking spectra going up and down as a function of the pixels, but with a different offset. And so glare mixes with diffuse reflectance in an uncontrollable way, and it influences the spectrum. So my algorithms will get confused because of it. So we need to do something there. Now, again, our hyperspectral camera setup takes an image and you immediately see what I mean with glare and specular reflection. Now, I see these intense spots. There are a few that are really saturating. So there, the specular reflection is so strong compared to the diffuse reflectance that it saturates the pixel of the camera. But there's a lot of areas where it's not saturating. And so, yeah, a saturating pixel doesn't give you any information. But here, in these areas where you have these whitish glow on the tissue, you still see the effect of glare in a quantitative manner, and it will screw up our spectral shape. Now, for instance, if I take all the spectra in this region of interest, you'll be looking at distribution of spectra that roughly looks like this. So the only thing that varies, there's some slight spectral variations, not much, but the main variation is the sort of an offset, and that has to do with the variation in surface orientation of each pixel. Now, an often used approach is the so-called Snv normalization, which is simply a mathematical procedure to generate, to turn this set of spectra into a set of spectra where the average is 0 and the standard deviation is 1. That sounds a bit odd, but if you do not consider this as data with a physical meaning, then you can just do this. And that is a way to get rid of the glare, but you also get rid of some of the scattering information. So yes, you could use this, but from a physics point of view, you don't like it. So basically, the Snv normalization removes glare, but also removes the absolute intensity of the spectrum and therefore the relation to the scattering intensity. And it removes all refractive index information and all surface structure information. Because what I see here, this variation may still give information on the sample. Another point is, especially when you try to develop a hyperspectral endoscope, for instance, and a clinician has to look to your device. This is an image where there's hardly any surface structure, and mainly diffuse light. You see some sharp edges, but if you would only see this, it's very hard to focus your eyes on it because it's only diffuse light. Here you have a lot of diffuse light coming from the depth of the skin, but on top of the skin are all these wrinkles and hairs, and the eye has an easy time focusing on these little surface structures. So this feels good to the eye, it's relaxed, you have the feeling that you're in control, that you can look sharp, and in the meantime, you can interpret the color information coming from the diffuse light. So we do not want to throw away all our surface reflection information, all our glare information, because it has been argued that you may be able to get rid of surface reflection by cross-polarization filters, for instance. That is only true to a certain degree, but if you find the perfect way of dumping all surface reflection information, you would be looking at very diffuse images, and clinicians would not be happy with it because they cannot focus. Okay, now let's do an experiment. So we have our camera, we have our tissue, and we have a light source. We shine light on it. We have specular reflection. We have our camera smartly oriented, so the saturating large amount of specular reflection is not seen by the camera. We have some glare going in the same directions, but also in other directions. And we have, of course, our diffuse reflectors. Now, the camera will detect the glare and the subdiffuse reflectors. Now I move my light source. I look under a different angle. And because I'm a smart guy, my specular reflection is still missing the lens of the camera, so I can still see glare and subterfuge reflectance. And I do that for a third time. So now I have 3 images with different amounts of glare and probably similar amounts of diffuse light. Now, so by varying the illumination angle, you may be able to vary the contribution of glare. And to illustrate that, these are some results. You see the differences are very subtle. But if you really look at a pixel-to-pixel basis, you will see white spots here that are not whitish here. So by comparing these 3 images, you can easily separate the glare and the diffuse reflection. And that will lead to an image like this, where we see the image with the glare and the image with the reduced glare. So here you see hardly any glare left. And because we have the glareless image, we can also calculate what we removed, and which is basically the glare that we removed. And this gives you a very, you see it, the surface structure that is reflected from the glare image is not the same everywhere. So here we have an area with hardly any glare, and here we have a very detailed variation of glare, which simply means that the surface structure here has many details and here it hasn't. So that tells you something about what is going on in the tissue. In fact, I believe, but this is ongoing research, I believe the fact that in the bottom part the surface is so flat, there is so little glare, that that part of the tissue may be softer. So there is no fine structure possible, because maybe this is just fatty tissue, and maybe this is indicative of more rigid tissue, and that could be helpful in identifying the diagnosis of tissue. For instance, if you look at this sample, which was taken from a patient and which was sectioned through, so basically you're looking at the tumor here. So this is the tumor tissue. And the other halves, the other parts are normal breast tissue. And as I said, normal breast tissue is fattier. Fat is soft. The tumor, surgeons know they can find tumors during surgery simply by feeling around. Tumors, surgeons describe it as finding the marble in the sponge. So the tumor is more rigid. You can see it after cutting, it has very detailed surface structure, probably because of the cutting movement of the knife. In fact, you don't see that. So the amount of glare may be related to the mechanical properties of the sample. But as I said, this is ongoing research, and we can't make any strong conclusions on this yet. Now, where do we apply this? So we apply this in breast cancer surgery at the moment. Now, you have 2 situations when you have a patient with breast cancer. One case where they have no metastasis. Those tumors can be treated with surgery. Previously, so I'm talking about 10, 15 years ago, the entire breast would be removed, and that's not a nice idea, but it would have excellent survival. So the problem would be gone, except in a few cases where the diagnosis was wrong and there was already a metastasis present in the patient, but they missed it. So if you have a metastasis, then the tumor has spread to other parts of the body. And even if you can treat the primary tumor, you have a systemic disease, and it's a completely different ballgame with chemotherapy. But the outlook for metastasized breast cancer is much worse than for people who do not have metastasis and can be treated excellently with surgery. But in the last decade, surgeons started to do breast conserving surgery, which means that they were not removing the entire breast, but just a small lump around the tumor. And then the challenge exists to find the proper boundaries of the tumor. Now that appears to be extremely difficult. Now we have, at the moment, we have roughly 500,000 breast conserving surgeries annually in Europe and the United States. And what happens is that after the surgery, the tissue that is removed from the patient is sent to the pathologist, and he cuts it up and looks at all aspects of the sample to see if there is tumor left in the margin, because if in the margin of the resection there is tumors, there's a fair chance on the other side of the margin that is still in the patient, there's also tumor cells. That happens roughly in 37% of the cases. It varies a little bit. In the United States, they have more recurrences because the surgeons are more breast conserving because cosmetic result is more important. In Europe, it's a little bit lower, but yeah, it varies from center to center. And what happens then is that you get additional radiotherapy or even additional surgery. This is a nightmare for the patient because they tell you you have breast cancer, you do the surgery, and then after the surgery, you have to wait a week. And then in 30% of the cases, they say, no, not good, not nice. So it's a dilemma for the surgery. If you want to perform better, you remove more, and that gives a bad cosmetic result, which may not be the biggest problem if you're 85, but especially for the younger women, it is a big problem. All this additional treatments costs a lot, and there's a lot of indirect costs because of the stress and the trauma, the plastic surgery, and the extra time off from work, etc. But this is quite a problem that we would like to solve for financial reasons, but mainly for because it's such a burden to the patient. Now, to give you an impression of how difficult it is, this is the problem. Now, we have had some dramatic progress in pre-operative imaging, and there's very good X-rays hanging on the wall of the operating room, but they don't tell you where the tumor is when you have to cut it out. I already said one of the strategies for the surgeon is to stick his finger in this open wound and feel around where the marble in the sponge is. But if what you cut out is too small, then the patient has to come back for additional treatment. But when you cut out too much, then yeah, maybe you cut too much. It's not good for cosmetic for the cosmetic results. So this is a dilemma for each surgeon in each procedure, and they are begging for extra information. Now, at the moment, the workflow during surgery is as follows. The surgeon does what he can to remove the sample as good as possible. That sample is going to the pathologist. Basically, the surgeon leaves some marks on the sample, and the pathologist paints it on the outside with standard color code. Then they slice it, and they look for the slice that goes straight through the tumor. And then they do some staining of the tumor, they fix it in formalin, and they make 10 micrometer slides of it, and they stain the tissue chemically. So there is the paint on the outside that tells you where exactly you're looking at, which side of the sample you're looking at, and then there's the chemical stain that stains the cells and the tissue structures differently, so you can see something under the microscope. Normal tissue that you cut in 10 micron slice is just transparent. And after this chemical staining, you see these beautiful images with different types of tissue. And then the pathologist looks at it and then comes up with his verdict. And then 3 to 10 days after the procedure, the patient gets the result. And that means, yeah, extra some additional surgery or maybe radiotherapy. In both cases, the patient is not very happy. So if you could do this, cut down on this 3 to 10 days, if you could make this 3 to 10 minutes, then the surgeon could be very conservative in his surgery, check if he left something and then take a little nibble more and another nibble more. He could do a much better job before the patient is surgically closed and sent home, rather than wait 10 days and then, yeah, you don't want to reoperate unless you really have to. And it's radiotherapy, which is also no fun. So here there's a real nice opportunity for hyperspectral imaging or fiber optic spectroscopy or whatever. So our experimental approach was the following. So the sample is removed and it is colored, painted by the pathologist. They cut in slices. Problem with doing clinical research is that you're not allowed to do something funny that changes the outlook of the patient. So you cannot disturb the workflow in the clinic unless you're very sure of what you're doing. But you need convincing data, and before you have them, you have to follow the lines of everyday work in the hospital. So we have these slices, and then we say, can we borrow them for 10 minutes? Now, that was allowed if we don't cut it, stain it, or ruin it in any other ways. So what we do is we put it in a little plastic cassette with black rubber below it. We do our hyperspectral imaging. Then we send it back to the pathologist and he does his stand-up work. The pathologist has stained it and then he performs his diagnosis. He draws in, basically this is what we made of it, but the pathologist takes this kind of slide and then with a pen draws in where the tumor is and where all kind of other tissues are. So we did not disturb the workflow for the patient, and we did have our images. Now, what the first things we saw is that when we take a region of interest in the tumor or in a piece of fat or in glandular tissue or carcinoma in situ, you see very distinct spectra. So that was very interesting. Basically the same thing we saw with our biopsy needle. This was done with our hyperspectral camera. So just imaging this slice of tissue. So yes, this is very hopeful that these basic tissue types give indeed very different types of spectra. And again, you can see here the adipose tissue, which is the normal fatty breast tissue, has this much stronger fat absorption band than the other tissues. And especially the invasive carcinoma and the carcinoma in situ, we see the fat absorption band is nearly absent. In these, there is a little bit left, and that is because the ductal carcinoma in situ is a more diffuse form of the cancer, where there still may be fat in between the cancer cells. Okay, now we did a whole lot of these samples, and then started to train with artificial intelligence. Yes, I'm sorry, not much biomedical optics in here, and that is because we realized that it's not subdiffuse, it's not diffuse, there's glare, etc. We are working on ways of doing this better, or of getting rid of the glare in a more sophisticated way, so we don't have to do what you may have noticed, this standard normal variant normalization. This is work of a few years ago. We are working on more advanced approaches where we don't throw away all the prior knowledge we have, but at this moment we had to. Machine learning in a sort of a standard way, and what you get then is an algorithm. As we have a white light image to show you what the sample looks like. We have the pathology image after the pathologist has annotated it with different colors, we know what the different tissue types are, and our hyperspectral image gone through our classification image generates an image like this, which is not too bad. There's a very large similarity between the two. So again, we're not there yet, but it's looking good. Now, looking in more detail, you see here a very well-defined tumor microscopically, but on your hyperspectral image, you see this yellowish region, which is basically in between clear tumor and clear normal. And why are we so uncertain about the boundaries? Well, that is something we have to, it's the same story here with this big solid tumor. The problem is not so big because the boundary region is small, but when you have these more diffuse tumors, which is called ductal carcinoma in situ, yeah, you have much more boundary regions and therefore much more uncertainty. And where does that come from? Well, it is related to the diffuse nature of the light. So even if the boundary between cancer and normal tissue is extremely sharp, light measured on one or on the other side of this boundary will have been scattered around the region. So the signature you get from tissue close to the boundary will have the signature of the entire region. And the entire region is a little cancer and a little normal mixed together. So these uncertain areas are inherent to the method. And it's even described in more detail here, where we did not diagnose per pixel, but defined pockets of 2, 16, 64, 144 pixels. And then you see that the accuracy is extremely good when we have large pockets, but then when we go to smaller pockets, then yeah, it's still easy to find fat, but the stuff we are looking for, invasive carcinoma and ductal carcinoma in situ, is really losing accuracy from pockets of 2 millimeter size, and it's the same with the connective tissue, and that is roughly our diffusion length. So we're looking with a microscope to the tissue with a spatial resolution of 2 millimeter. No matter how many pixels our camera has, the image is not sharper than 2 millimeters, and therefore we shouldn't try to diagnose more sharper. Now, if you do all the work, we had you see on all these samples, we had an humongous number of pixels, and those were so pockets of 2 by 2 millimeters in this case, an enormous number, and then you get yeah, very good accuracy for finding cancer, reasonable to good accuracy for finding ductal carcinoma in situ, so the more diffuse type of cancer. Yeah, we can distinguish it excellently from fat and connective tissue, and it's not perfect. Is that a problem? Aren't we doing something immoral? Aren't we coming up with technology that will send 5 out of 100 patients with cancer back home? Well, as you know, when the surgeon does it by his finger, feeling around, and by his eye, he sends 37% of the patients home while they still have some cancer in their body. So with this technique, we might do a lot better. And as a surgical aid, well, there's always the surgeon. It's a 2-stage rocket, so it's improving the eye of the patient, of the surgeon. So we could really improve the procedure doing this. But again, this was done on samples that are lying outside the patient and are already at the pathologist's office. So you really have to do this fast. or the patient would be lying half an hour longer on the operating room, which is not acceptable for many reasons. So you need to do this either in the operating room or in vivo. Now, there's another complication here because, as I said, we measured on the slices where you could look at the tumor directly. And if you have a lump, you want to do it fast, you have to image the lump on the outside. There's no doubt that there is a tumor inside this lump that you have removed. The question is, are there cancer cells on the outside of the lump? Because if you find cancer cells on the outside of the lump, there may be cancer cells left in the patient. Now, then we started scanning these lumps because that is a little bit closer to the clinical question. So it's a little piece of tissue. We put it on our scanning system and we scan it 6 times like it is a cube. We just turned it around 90 degrees and then the side and then the upper side and the lower side. And we have 6 scans. And then on these scan images, we apply our algorithm. Basically, this is how these 6 scans then look, one sample, for instance. And if you then apply the algorithm, yeah, you do see some positive margins. So again, this is encouraging, but it's not very practical in the sense that it takes a lot of time doing these 6 scans. You're not quite sure where it is, and you know what you see here may also be the same as here because the tissue deforms. So yeah, although it's encouraging, it's not the final answer. So it could be fast enough, but yeah. In fact, we started 2 parallel lines here. The one is that we try to automate this scanning approach, and that proved to be extremely difficult because calibration of the camera is pretty simple when you have a flatbed scanner, because you have a reference standard also present next to the sample and you do the scan in one time. Now, if you do a 3D scanner, you have to, we spent 3 years on it trying to build a 3D scanner, and it is really, really cumbersome. So we stopped doing that and we moved on to doing this in vivo. So not measure the lump, but measure on the side of the resection margin that remains in the patient, because there is where you want to know if there's tumors. Again, you can imagine how difficult it is to do hyperspectral imaging here. It's basically not very practical. So you would need some kind of hand probe to do this, and yeah, you need to repeat different locations. You can image it from above, but you wouldn't be able to look into this little hole, or there would be, I don't know, illuminating lights, or it would be on the bottom side, or this is not easy to image. So we went back to our fiber optic approach, and you could say this is a 6-pixel imaging, hyperspectral imaging device. We have 6 light sources that switch on one by one, and in the middle we have a detection fiber with a spectrometer. So basically we take 6 spectra with source detector distance 2 millimeters in this case, and with that we sample a volume of roughly 6 millimeter in diameter. And with that you can simply move around through the wound and investigate suspicious locations. Now, this is where it ends, because this is really work in progress. One of the problems with our fiber optic device was that it took 20 seconds to take 6 scans out of 6 fibers. We worked with that on ex vivo tissue samples, but surgeons are way too impatient to do a multiple 20-second scans. So we had to build a new device. Now, luckily, they're very nice fiber optic light sources now, so you don't have to use the tiny bit of light of a halogen lamp. You can get into an optical fiber, but you can use a fiber laser. And now we can do these measurements within 2 seconds, basically. And that device is at the edge of going into the clinic. And then we will have real-time measurements. And yeah, that's if you fail to your exam and you have to follow the course again next year, then you may see some early results. That's not a reason to fail the exam, but if you're interested, keep track of what is going. Okay, thank you very much. This is where my story ends. And if necessary, I can answer any question.
Dankjewel, Dick. I don't see any questions online.
Everybody asleep?
I guess.
Okay, well, if there are questions, you can also mail me. Dirk can help you get my email address.
All right.
Okay?
Dankjewel.
Okay, pleasure.
Thank you.
Okay, see you next time.
Thank you.
Bye.
Thank you.